Alright, this is the second part of the video. What I've done, I've just inserted an inductor in line with the resistive load. And also I have added a freewheeling diode. That's to make sure the current will continue when that switch is open. And that's very important and necessary for our circuit in order to protect the switching device and also to pass the current through while the switch is open. Now I have chosen a value of 100 microhenry as a start to see the effect of that inductor on the output current and output voltage. And we will repeat the same procedures what we have done in the resistive load again and see the effect of that inductor while increasing the frequency, switching frequency and the pulse width modulation or duty cycle on the output performance. Let's start and see what's going on. I have started again back when the first thing we will do is just say I selected the frequency of 20 Hertz and the duty cycle of 50%, and we will press start and see the results again. Now coming back to the values of the average voltage and the RMS voltage, it's gonna be the same. There's nothing changed. Let's look at the oscilloscope, and also it's gonna be the same. There's not much change actually. I can see only a little change here, and that is because of the value of the inductor is relatively small. And if we look back to the currents, is the same as it was. If there is only a resistive load, that means there's not much effect of the inductive load on the output currents and the output voltage. It's almost similar to the resistive load alone, as if it was working alone. So this 10 amps again is the same for the average value of the current, and this is the 14.14 is the RMS value of the output currents. Now let's start increasing the inductance value. This is one of the methods actually we can play around with in order to minimize the ripple. The objective here is to minimize the ripple of the current, because if we go back and look back at the current, we can see it goes up to 20 amps and back to zero, then again to 20 amps and back to zero. This is not going to be beneficial for any types of loads. So we need to have an almost fixed pure DC current, and that's if we can achieve. And one of the methods we can do is by increasing the inductance value. Let's see if we put one digit over here, and I will keep the same value for the duty cycle, and the switching frequency is the same. And we will do this, run the simulation again, and we will see the effect on that. Alright, as you can see, there's a slight change as well on the ramping up of the voltage and the current, but that not much different actually, and the effect is minimum. Is, as you can see here, is the current, the voltage is around 50, and the voltage is around 50, and the current is around 10 amps, still the same, not much change. Now I will increase the inductance value again, so another digits. So let's see what's gonna happen again and see the value or the effect. Oh, now it's going to change. As we can see here, the rising of the voltage and the current is also changed because of the inductance value has increased. But looking at the average current voltage and the average current is nearly the same, not much change. And I will increase by another digits, and let's see what's gonna happen. All right, I guess there's a big change now. As you can see here, almost the average value of the voltage equals to the average value of the RMS, equals to the RMS value of the voltage, which means that the average value is equal to the RMS, and this means that is a good achievement. Also, the current has changed here, which are almost the same. And let's look at the oscilloscope and see the waveforms. Yes, it's a big difference actually. All right, what I'm gonna do is, because I think the period of running the simulation is too slow, it's too small, and I will increase it to 0.5 and see what's gonna happen. It's gonna increase a little bit, but I think we will have a better view on the cycles. Yes, if we have a look here, we will see the voltage. It's going between 75 value, the peak value, and the minimum value is up to down to 22, which is good. And the current as well, the maximum value is around 15 and the minimum value is around 4. If we keep increasing the inductance, we will get better performance though. Let's see what's gonna happen again. I think we can also minimize the ripple. Let's see if we can put that to 2. So 0.2 farad is a big value though, but it's just a simulation, and we will see what's gonna happen. Yes, we have even better voltage and better current. If the maximum voltage is around 65 and the minimum is down to 35 volt, and whereas the current is 13 and the minimum value is 7. Again, look back at the average, is always the same, it's not changing actually, but the B value is changing and the minimum value is changing, which gives us a lower ripple. And that goes well with the results. As you can see here, the average value is equal to the RMS value of the voltage, and also the average value of the current is equal to the RMS value. But what we have done here is that we have increased the inductance value to a value that is not really reasonable in our practical life. It's finding an inductor with that value is going to be a very big problem. So even though we cannot achieve it, is 0.2 Henry. That's too much. So what we will do is we will go back again to 100 microhenry, the value of 100 microhenry, and we will start increasing the switching frequency. So this is 100 microhenry, that's the initial value, and let's see the results again before we start increasing the switching frequency. Now again, as we can see here, the average value is 50, the RMS value of the voltage is 70, the average value of the current 10, and the RMS value is 15, almost 14, and the waveform is almost rectangular or square. So there's not much effect with that value. So what we will do, I will increase the switching frequency while keeping the duty cycle the same. So I'll increase it to 200 Hertz. And of course I have to change the period for calculating the mean value to be consistent with the pulse generator frequency. And we will run the simulation and see the output results. It will take a little bit of time. Yes, and we will look at the switching frequency. Again, it's the same, not that much change. although there is a at the edges here we can see the rising and falling is changing, but the results is the same, 50, 10, and the RMS is the same. We will see, we will increase it again while keeping the inductor value is the same. We will just keep increasing the frequency step by step. So now we are increasing the frequency up to 2000 hertz. And of course we have to change the period. Integrating period here is to 2000, and then this one to 2000. And we will run the simulation again. After we finish this simulation, we will see the effect of increasing the pulse width modulation actually, and see how we can change the average value while fixing or keeping the frequency, the switching frequency constant. Yeah, it's taken a little bit of time. Yes, now it's finished. Let's see. Let's have a look. Let's have a look at the, yes, I think it's changing. Yeah, the waveform is changing a bit, but still the average value is not changing here. Almost 67, and here is the RMS is 13.5956. Now I think if I change the frequency up to 20 kilohertz, now we will see a great change actually. We will see a big difference, and we will show you in a minute the results after we have increased the frequency up to 20 kilohertz. But I need to decrease the time a little bit just to shorten the simulation running time, make it quicker. So what does that tell me actually? Actually, it tells me that I don't need to get a big value of inductor. It's very, very difficult, very hard to get that big value of inductor. Whereas what I can do is just by designing a controller circuit, like I can use Arduino, I can use peak microcontrollers or any other digital devices to generate such a frequency or a high digital frequency up to 20-25 kilohertz, and then I can achieve a very good result with that. I can minimize the ripple while having a very low or considerable value of inductor rather than just increasing the value of inductor. And this will make my circuit smaller, and I think maybe this is gonna be best way of better way of solution. Let's have a look and see. Yes, great. Now, as you can see here, this is the voltage, and the maximum value has gone up to 75, and the minimum value up to down to 25, whereas the current has gone to 15 and the minimum value up to down to 5, which is a good achievement actually. And we have minimized the ripple of the voltage and the ripple of the current actually. And as we can see here, there's a big difference from the previous one, especially in the RMS value. It's becoming closer to the average value. And also the RMS current is coming closer to the average value of the current. Now, what I will do, instead of keep increasing the frequency and going higher beyond 20 kilohertz, because increasing the frequency, although that it will solve my problem, in terms of minimizing the ripple of the current, especially the current ripple. But the problem is, the higher is the switching frequency, is the higher of the switching losses. Well, this is going to be then a disadvantage for the switching device. So what I will do, I will introduce a capacitor across the load, and after that was gonna come after the inductor. So it's gonna work like as a low pass filter, and it will minimize the ripple of the voltage as well. So what I will do, I will just put a small value of the inductor, is 5 microfarad, as we can see here, and see what's the effect, what's gonna be the effect of that capacitor on the output performance and the oscilloscope, the waveforms, and the output voltages. Just remember the values here is the RMS value of the voltage and the RMS value of the current and the waveform. Just have a final look before we run the simulation and see the difference. So remember, this is the peak value of the current, the voltage, and the peak value of the current. And let's run the simulation again with the capacitor and see the results. Yes, I think by looking at the display here, we can see there is a good achievement actually. Also here on the current side, we also have a good achievement. Let's talk about this part of the oscilloscope or the displays. Here are the part that is related to the current of the supply. So if you want to calculate the supply current, you can measure it or you can see it out there, and you can also the waveform. I will show you the waveform of the supply current in here in a minute. Once we finish that, and we will see. After that, well, I will show you also what will happen if I increase the duty cycle, and we will see the effect on the average values and on the RMS values as well, and on the waveforms through the oscilloscope. Alright, it's finished now. Alright, it's great achievement actually, just by adding a small capacitor. Relatively, it's a small one, so if you see here, it has minimized the ripple of the voltage, so the peak-to-peak value is around 20, and also it has minimized the ripple value on the current as well accordingly, so the peak-to-peak value is around 4 amps. That's a good achievement actually, and let's see what's gonna happen if I increase the duty cycle. Just increasing the duty cycle here by 75%, up to 75%, and we run the simulation again and we will see the results. Yes, if you look at here, this is the average value, is the same as we had it in the resistive load, so it's almost 75%, and the RMS value is almost the same of the voltage, also of the current. That tells me that we have got a very nice achievement by using a combination between the inductor and the capacitor, which will give us a minimized ripple of the voltage and a minimized ripple of the current as well, which will be good for many applications and many loads in our practical life or in implementation. Alright, I'm gonna have a look at the source current as well and see what's the shape of that value of the waveform. Once we finish, we will have a look at that one. Yes, it's nearly done. Yes. Again, let's have a look. So the waveform is the same. Yes. The peak value is around 10 volts V peak to peak, and the current is around 4 amps. The average value is 75 of the voltage, and the average value of the current is 15. The RMS is 15 as well. Let's have a look at the supply current. How does it look like? Oh yes. Now, why is that? Why it's going like that? If we look at this part, this is the time or the interval when the switch is off. That means the supply doesn't pass any current to the load, which is normal to see this kind of waveform, whereas only the part that is conducting and having a current from the power supply or the source is that part, which is that interval is the time on, which is 75%, whereas it's 0 on that part. The average value of that supply current is around 11.3 amps, the average value of the current, whereas in the output current is the average value is around 15. The RMS value is around of the current is around 14 amps, whereas the RMS value of the output current is around 50. Now, with this simulation, I think we can stop, and on the other videos I will show you the boost converters and how can we manipulate the duty cycle and also the frequency in order to achieve the higher voltages for certain applications. Thank you very much. We'll see you again. Bye.